Chemical equilibrium is the thermodynamic equilibrium of a system consisted of the reactants and products of a reversible reaction. For example, dinitrogen tetroxide and nitrogen dioxide convert between each other in a reversible reaction. Thus, they form an equilibrium mixture in any condition. At very low temperature, dinitrogen tetroxide is dominant, and the mixture is colorless. As temperature rises, the fraction of nitrogen increases, and the mixture becomes brownish-yellow. At chemical equilibrium, reactants and products are present in states which have no further tendency to change with time, so that there is no observable change in the system. Chemical equilibrium results when the forward reaction proceeds at the same rate as the reverse reaction. Such a state is known as dynamic equilibrium. Consider a general reversible reaction, in which the reactants and products are denoted by A and B respectively. The Gibbs free energy of the reaction at certain temperature can be calculated from the difference in the total chemical potentials of the products and the reactants. The chemical potential of each substance can be calculated from its standard chemical potential and activity. The standard chemical potential is equal to the standard molar Gibbs free energy. Then, combine all the standard Gibbs free energies. The result is the standard Gibbs free energy of reaction. Also combine all the activities to form reaction quotient, which is the ratio of the activities of the product species over those of the reactant species involved in the chemical reaction, taking stoichiometric coefficients of the reaction into account as exponents. Thus, reaction Gibbs free energy is determined by the standard Gibbs free energy of reaction and corrected by the reaction quotient. The Gibbs free energy of reaction increases with the activities of the products and decreases with the activities of the reactants. When the Gibbs free energy of reaction is negative, the forward reaction is spontaneous. When the Gibbs free energy of reaction is positive, the backward reaction is spontaneous. Let's use the formation of ammonia as an example. The standard Gibbs free energy of reaction is twice the standard Gibbs free energy of formation of ammonia, which is negative. When the activities of all the substances are 1, the Gibbs free energy of reaction is negative, and the forward reaction is spontaneous. That is, more ammonia is produced. When the activities of nitrogen and hydrogen are 0.1, while the activity of ammonia is 10, the Gibbs free energy of reaction becomes positive, and the backward reaction becomes spontaneous. That is, more ammonia decomposes. When the chemical reaction is in equilibrium, the Gibbs free energy of reaction is 0. The reaction quotient in equilibrium is defined to be the equilibrium constant. Thus, the equilibrium constant is related to the standard Gibbs free energy of reaction. The Gibbs free energy of reaction depends on the ratio between the reaction quotient and equilibrium constant. If the reaction quotient is greater than the equilibrium constant, the reaction Gibbs free energy is positive, and the backward reaction is spontaneous. If the reaction quotient is smaller than the equilibrium constant, the reaction Gibbs free energy is negative, and the forward reaction is spontaneous. For example, let's have a look at the formation of ammonia again. In industry, ammonia mass production uses Haber process, in which iron-based alloys are used as the catalysts. Suppose the gases are all ideal and the partial pressures of nitrogen and hydrogen are 25 bar and 75 bar respectively. Find the partial pressure of ammonia in equilibrium. The standard Gibbs free energy of reaction can be calculated with the standard enthalpy of reaction and standard entropy of reaction. Its equilibrium constant can be calculated from the standard Gibbs free energy of reaction. From the expression of equilibrium constant, the activity of ammonia can be calculated from the equilibrium constant and the activities of nitrogen and hydrogen. The activities of nitrogen and hydrogen are calculated from their partial pressures. Finally, the activity of ammonia can be converted to its partial pressure. In practice, the partial pressure of ammonia cannot reach this value because the reaction is slow and the ammonia is continuously removed from the reactor. Solubility equilibrium can be regarded as a special type of chemical equilibrium that exists when a substance in the solid state is in equilibrium with the solute in a solution. Here, we do not discuss the solutes which dissociate upon dissolution. The equilibrium constant is the ratio between the activity of the saturated solute and the activity of undissolved solid. The activity of a pure solid is 1. So, the equilibrium constant is equal to the activity of the saturated solute. Meanwhile, the activity of the solute is its relative concentration compared to the standard concentration, corrected by the activity coefficient. The activity coefficient is a factor used to account for deviations from ideal behavior in a mixture of substances. In an ideal solution, the activity coefficient of the solute is 1. Here, we use the dissolution of sucrose in water as an example. The activity of dissolved sucrose is equal to the equilibrium constant. The standard Gibbs free energy of dissolution can be calculated from the equilibrium constant. By the way, the numerical value of the molarity of sucrose of a saturated solution in mole per liter is much higher than its activity. That is because the saturated sucrose solution is too concentrated to be ideal. The activity coefficient is significantly smaller than 1. Finally, let's consider the temperature dependence of equilibrium constant. Rearrange the relation between equilibrium constant and standard Gibbs free energy. Differentiate the equation with respect to temperature. The right side can be replaced with the Gibbs-Helmholtz equation. We get the relationship between the equilibrium constant and the standard enthalpy of reaction. It is called the Van't Hoff equation. From Van't Hoff equation we can find that, when temperature rises, the equilibrium constant of endothermic reaction increases. We say, the equilibrium of endothermic reaction moves forward as temperature rises. Meanwhile, the equilibrium constant of exothermic reaction decreases. That is, the equilibrium of exothermic reaction moves backward as temperature rises. The Le Chatelier's principle is a principle used to predict the effect of a change in conditions on chemical equilibria. It states that, when any system at equilibrium is subject to change in any state function, the system changes to a new equilibrium and this change partly counteracts the applied change in that state function. For example, the equilibrium between dinitrogen tetroxide and nitrogen dioxide. When the concentration of nitrogen dioxide is increased, the reaction quotient decreases and becomes smaller than the equilibrium constant. The reaction moves forward to consume some nitrogen dioxide. The concentration increase of nitrogen dioxide is partly counteracted. When the concentration of nitrogen dioxide is decreased, the reaction quotient increases and becomes greater than the equilibrium constant. The reaction moves backward to produce more nitrogen dioxide. The concentration decrease of nitrogen dioxide is partly counteracted. The same processes happen when the concentration of dinitrogen tetroxide is changed. The effects of change in temperature and volume can be analyzed in a similar way. For endothermic reaction, treat thermal energy as a reactant. For exothermic reaction, treat thermal energy as a product. If the volume increases during the reaction at constant pressure, treat volume as a reactant. Otherwise, treat volume as a product. For example, the formation of dinitrogen tetroxide is exothermic, and the volume decreases. When the temperature rises, the equilibrium constant lowers. The equilibrium moves backward to consume some thermal energy. The thermal energy increase is partly counteracted, vice versa. When the volume increases, the reaction quotient increases and becomes greater than the equilibrium constant. That is because the decrease of the concentration of nitrogen dioxide is squared, while the decrease of the concentration of dinitrogen tetroxide is linear. The reaction moves backward to consume some volume. The volume increase is partly counteracted, vice versa.